Right now, above you, photons that left a distant star thousands of years ago are arriving at Earth. Some of those photons are entering your eyes at this very moment, carrying information across impossible distances, traveling without pause through the vacuum of space. Stars have been doing this for billions of years. They'll continue long after we're gone. There's something quietly reassuring about that. Tonight, we're going to explore the most calming, gentle facts about stars. Not the explosive ones, not the dramatic endings, but the steady, patient, enduring truths about these distant points of light. The facts that remind us of continuity, of vast scales that make our worries small, of processes so slow and so reliable that they've outlasted entire civilizations. We'll move through this together slowly, without rush, covering everything from how stars form to how they live their impossibly long lives, to the gentle ways they shape the cosmos around them. There's no need to remember everything. No need to stay alert. This is simply a quiet tour through some of the most calming, perspective-giving truths about the stars above us and around us. You can listen as long as you'd like, or let the words settle into the background as you rest. Let's begin where all stars begin, in the cold, quiet dark. Somewhere in the universe right now, in a region of space so dim that no human eye could see it without help, a cloud is collapsing. It's made of hydrogen and helium, mostly. The simplest elements, the first elements, the building blocks left over from the beginning of everything. This cloud has been drifting through space for millions of years, perhaps billions, growing denser in some places, thinner in others. And now, slowly, almost imperceptibly, gravity is winning. The cloud is contracting, particles are pulling closer together, heat is beginning to build. This is how stars are born. Not in dramatic explosions or sudden flashes, but in a slow, quiet accumulation of matter that takes tens of thousands or even millions of years. There is no violence in this beginning, just gentle collapse, the patient gathering of hydrogen and dust, and the deep, invisible work of gravity. Tonight, we're going to explore the most calming, comforting facts about stars. The things that make them not just distant lights, but slow, patient, predictable companions in a universe that is far more stable than we often imagine. We'll talk about how they form, how they live, how they shine, and what their presence means across the long, quiet expanse of cosmic time. This will be a slow journey. There's no rush. You can listen all the way through or let your mind drift wherever it needs to go. Either way, the stars will still be there, doing exactly what they've been doing for billions of years. Let's begin. A star is a sphere of gas held together by its own gravity, producing light and heat through nuclear fusion in its core. That's the simple version. But even that simple version contains something quietly extraordinary. A star is a place where gravity and pressure reach such perfect balance that hydrogen atoms, the simplest and most abundant element in the universe, are forced together so tightly they merge into helium and release energy in the process. This process is called nuclear fusion, and it's happening right now in the core of the Sun, about 93 million miles from where you are. It's also happening in the cores of hundreds of billions of other stars in the Milky Way, and in trillions upon trillions more across the observable universe. The core of a star like the Sun reaches temperatures around 15 million degrees Celsius. That's 15 million. Not 15,000, not 1,500,000, 15 million. At that temperature, atoms move so fast that when they collide, they don't just bounce off each other. They stick, they fuse, and when they do, a tiny amount of mass is converted into energy, following Einstein's equation, E equals mc squared. That energy radiates outward, takes hundreds of thousands of years to work its way up through the dense layers of the star, and eventually reaches the surface, where it's released as light. That light crosses space. Some of it reaches Earth. Some of it reaches your eyes. And in that moment, you're connected to a process that's been running continuously for 4.5 billion years. Stars are not explosions. They're not fires. They're ongoing reactions held in equilibrium by forces that balance each other with extraordinary precision. Gravity pulls inward. Pressure from the heat of fusion pushes outward. For most of a star's life, these forces are equal. The star doesn't collapse. It doesn't explode. It just shines. And it does this for a very, very long time. Our sun, for example, has been shining for about 4.6 billion years. It's expected to continue shining in much the same way it does now for another 5 billion years or so. That's a total lifespan of nearly 10 billion years. For comparison, modern humans, Homo sapiens, have existed for around 300,000 years. Recorded human history covers maybe 5,000 years. The entire span of complex life on Earth is around 500 million years. The sun predates all of it and will outlast almost all of it. That kind of stability is hard to fully grasp, but it's worth sitting with for a moment. Stars are not fragile. They are not fleeting. They are engines of fusion that run on timescales so long that entire civilizations, entire species, entire evolutionary epochs rise and fall in what is, to a star, barely a moment. The light from a star is also remarkably consistent. The sun's brightness varies by less than 0.1% over the course of its 11-year solar cycle. Yes, there are sunspots. Yes, there are solar flares. But the total energy output, the luminosity, stays almost perfectly steady. This steadiness is one reason life was able to develop on Earth in the first place. A wildly variable star would make stable climates nearly impossible. But our sun is calm. It has been calm, and it will remain calm. Most stars in the universe are even calmer than the sun. The most common type of star is a red dwarf, a star with a mass between about 8% and 50% that of the sun. Red dwarfs burn their hydrogen fuel so slowly that they can shine for tens of billions, even hundreds of billions of years. Some red dwarfs that formed in the early universe are still in their infancy, relatively speaking. They've barely aged at all. Red dwarfs are also incredibly numerous. They make up roughly 70 to 80% of all stars in the Milky Way. Most stars in the universe are small, dim, cool, and extraordinarily long-lived. The dramatic, short-lived, brilliant blue giants we often picture when we think of stars are actually quite rare. The universe is not dominated by fireworks. It's dominated by embers, tiny, steady, patient lights that will burn long after everything else has faded. And these embers are everywhere. In our galaxy alone, there are an estimated 200 billion to 400 billion stars. In the observable universe, there are roughly 2 trillion galaxies. If each galaxy contains on average 100 billion stars, that gives us around 200 billion trillion stars in total. That's 2 followed by 23 zeros, 200 sextillion. Each one of those stars is a furnace. Each one is converting mass into light. Each one is holding itself together through the balance of gravity and pressure. And most of them are doing this quietly, steadily, without drama, across timescales that dwarf human comprehension. When you look up at the night sky and see a star, you're not just seeing a point of light. You're seeing the surface of a distant sun, a sphere of plasma larger than anything you'll ever stand on, powered by a reaction that has been running for billions of years and will continue running for billions more. You're seeing stability, you're seeing endurance, you're seeing a kind of cosmic patience that puts every human worry, every human ambition, every human fear into a perspective that is, if you let it, deeply calming. Stars don't hurry, they don't rush, they don't panic, they simply exist and shine and wait, and they'll still be there tomorrow. Stars are not created suddenly. They don't appear out of nothing. They form slowly over millions of years in regions of space where gas and dust have gathered in sufficient quantity to begin collapsing under their own gravity. These regions are called molecular clouds, and they're among the coldest, darkest, quietest places in the galaxy. A typical molecular cloud might span dozens or even hundreds of light years across and contain enough material to form thousands or even tens of thousands of stars. The temperature, the heat, inside these clouds is usually around 10 to 20 Kelvin. That's roughly negative 260 degrees Celsius. At these temperatures, most of the gas is hydrogen and much of it is in molecular form, H2. Molecular clouds are not uniform. They have dense clumps and thin regions. Over time, if a clump becomes dense enough, gravity begins to pull it inward. This process can be triggered by a nearby supernova shockwave, by the collision of two clouds, or simply by random fluctuations in density. Once it starts, it continues. As the clump collapses, it heats up. This is a consequence of gravitational energy being converted into thermal energy. The material falls inward, and as it does, the particles collide more frequently, moving faster, generating heat. At first, this heat radiates away into space. The cloud remains cool. But as the collapse continues and the core becomes denser, the heat begins to be trapped. The core temperature rises. This collapse is not fast. It can take hundreds of thousands of years, sometimes millions, for a collapsing cloud core to become a protostar, a hot, dense object that is not yet fusing hydrogen, but is on its way. A protostar is surrounded by a disk of gas and dust, called an accretion disk, which spirals inward, feeding material onto the growing star. This disk is where planets can eventually form. In our own solar system, the Sun formed from the center of such a disk, and the planets formed from the leftover material in the disk itself. During this phase, the protostar is often hidden from view, buried deep within the cloud that formed it. It emits light, but that light is absorbed by the surrounding dust and re-emitted as infrared radiation. This is why we often study star formation using infrared telescopes. They can see through the dust and reveal the warm protostars within. Eventually, the core of the protostar becomes hot enough and dense enough for nuclear fusion to begin. This happens when the core temperature reaches around 10 million Kelvin. At that point, hydrogen nuclei, protons, begin to fuse into helium, releasing energy. The protostar becomes a true star. This moment is not dramatic. There's no explosion, no sudden flash. Fusion begins gradually, and, as it does, the energy it produces creates an outward pressure that halts the collapse. The star reaches hydrostatic equilibrium, the balance between gravity pulling inward and pressure pushing outward. From this point on, the star will remain in this stable state for the vast majority of its life. For a star like the Sun, this stable phase, called the main sequence, lasts about 10 billion years. For smaller stars, it lasts even longer. For larger stars, it's shorter, but still measured in millions or tens of millions of years. What's striking about star formation is how orderly it is. Yes, the clouds are chaotic. Yes, there are turbulent flows and magnetic fields and complex interactions, but the end result is remarkably predictable. A clump of gas collapses. It heats up. It begins to rotate. it forms a disk, it ignites fusion, it becomes a star. This process has been happening since the universe was a few 100 million years old. The first stars, called population 3 stars, formed from clouds of hydrogen and helium, with no heavier elements at all, because no heavier elements existed yet. Those stars were massive, short-lived, and when they exploded as supernovae, they scattered heavier elements, carbon, oxygen, iron, into space, enriching the clouds that would form the next generation of stars. Our Sun is a third-generation star, or later. It contains elements forged in the cores of earlier stars. The calcium in your bones, the iron in your blood, the oxygen you breathe. These were all created inside stars that lived and died before the Sun was born. You are made of star material, not poetically, literally. And that process continues. Right now in the Orion Nebula, about 1,300 light-years from Earth, new stars are forming. The nebula is a vast molecular cloud glowing faintly in visible light and brightly in infrared. And within it, protostars are heating up, disks are forming, and in a few 100,000 years, new stars will ignite. Star formation is not an event, it's a process. A slow, patient, inevitable process that has been running for over 13 billion years and will continue for trillions more. And it happens in silence. Space has no air, no medium for sound to travel through. The collapse of a cloud, the birth of a star, the ignition of fusion, all of it happens without a sound. Just light, heat, and gravity working together in the dark. Once a star begins fusing hydrogen into helium in its core, it enters the main sequence, and this is where it will spend most of its life. For the Sun, that's about 10 billion years. For a red dwarf, it could be 100 billion years or more. For a massive blue star, it might be only 10 million years. But regardless of the duration, the main sequence is a time of stability. During this phase, the star is in hydrostatic equilibrium. Gravity pulls inward with a force proportional to the mass of the star. The pressure from the heat of fusion pushes outward with an equal force. These two forces balance perfectly, and the star neither collapses nor expands. It simply exists, shining steadily, consuming its hydrogen fuel at a rate determined by its mass and temperature. The Sun, for example, fuses about 600 million tons of hydrogen into helium every second. That sounds like a lot, and it is. But the Sun contains about 2 × 10 to the power of 30 kilograms of material. At its current rate of fusion, it has enough hydrogen in its core to continue shining for another 5 billion years. This is one of the most calming facts about stars. They operate on timescales so vast that even enormous rates of consumption translate into near-eternal endurance from a human perspective. The light a star produces during the main sequence comes from the energy released by fusion. When 4 hydrogen nuclei fuse into one helium nucleus, a small amount of mass is lost. That mass is converted into energy according to E equals mc². The energy is released as gamma-ray photons, which begin a long, slow journey outward from the core. The interior of a star is incredibly dense. Photons cannot travel far before being absorbed and re-emitted by atoms. They scatter, bounce, and diffuse outward in a random walk that can take hundreds of thousands of years. In the Sun, a photon produced in the core takes an average of 100,000 to 200,000 years to reach the surface. Once it reaches the surface, it escapes into space and travels in a straight line at the speed of light. This means that the light you see from the Sun today was produced in the core hundreds of thousands of years ago, during the time when early Homo sapiens were just beginning to spread across Africa. The energy itself is ancient, even though the light is only 8 minutes old by the time it reaches your eyes. The surface of a main sequence star is called the photosphere, and this is the layer we see when we look at a star. The Sun's photosphere has a temperature of about 5,700 Kelvin, which gives it a yellowish-white color. Hotter stars appear blue. Cooler stars appear red. The color of a star is a direct indicator of its surface temperature, which in turn is related to its mass. Massive stars are hotter and bluer. Low-mass stars are cooler and redder. This relationship is captured in the Hertzsprung-Russell diagram, a chart that plots stars by their luminosity and temperature. Most stars fall along a diagonal band called the main sequence, and a star's position on that band depends almost entirely on its mass. The Sun is a G-type main sequence star, also called a yellow dwarf, though it's not actually yellow, it's white. Its light only appears yellowish when filtered through Earth's atmosphere. In space, the Sun would look white to your eyes. Red dwarfs, the most common stars, are M-type stars. They're cooler, dimmer, and smaller than the Sun, with surface temperatures between 2,500 and 4,000 Kelvin. They're so dim that none of them are visible to the naked eye from Earth, even though they make up the majority of stars in the galaxy. Blue giants, the rare massive stars, are O-type or B-type stars. They have surface temperatures above 10,000 Kelvin, sometimes exceeding 30,000. They're incredibly luminous, some emit hundreds of thousands of times more light than the Sun, but they burn through their fuel quickly. A star with 20 times the mass of the Sun might only live for 10 million years. This creates an interesting contrast. The universe is full of faint, patient, long-lived red dwarfs that will outlast nearly everything. But when we look up at the night sky, the stars we see are often the rare, massive, short-lived giants because they're bright enough to be visible across vast distances. Our view of the stars is biased toward the dramatic, even though the reality is far quieter. The main sequence is also a time when planets, if they exist, have stable conditions. A star's luminosity changes very little during this phase. Its spectrum remains consistent. Its energy output is predictable. For a planet in the habitable zone, the region where liquid water can exist on the surface, this stability is essential. Earth has been in the Sun's habitable zone for billions of years, and the Sun's steadiness has allowed life to develop, evolve, and persist. Other main sequence stars likely host planets as well. We've discovered thousands of exoplanets, and many orbit main sequence stars similar to the Sun. Some orbit red dwarfs. A few orbit hotter, more massive stars, though those systems are less stable over long timescales. The main sequence is not eternal, but it's close. For the vast majority of a star's existence, this is where it lives. And during this time, it does one thing, and does it well. It shines. There's something deeply reassuring about that. Stars don't multitask, they don't get distracted, they don't have existential crises. They simply convert hydrogen into helium, release energy, and shine. And they do this for billions of years. The Sun has been doing this since before the Earth existed. It will continue doing this long after every human being alive today is gone. And somewhere out there, a red dwarf is doing the same thing, and it will keep doing it for 100 billion years. That kind of constancy is rare. In a universe full of change, stars are anchors. They are reliable, they are patient, they are calm, and they're always there even when we're not looking. When you look at a star, you're seeing light, but that light contains information. The color, the brightness, the spectrum, all of these reveal details about the star's temperature, composition, age, and motion. By studying starlight, astronomers can learn almost everything there is to know about a star without ever visiting it. The color of a star is determined by its surface temperature. This follows a principle called blackbody radiation, which describes how objects emit light based on their temperature. A hotter object emits more light at shorter wavelengths, which we perceive as blue. A cooler object emits more light at longer wavelengths, which we perceive as red. The hottest stars, with surface temperatures above 30,000 Kelvin, appear blue or blue-white. Stars like Rigel in the constellation Orion and Spica in Virgo are examples. These are massive, young stars that burn intensely and have short lifespans. The coolest stars, with surface temperatures below 3,500 Kelvin, appear red. Stars like Proxima Centauri, the closest star to the Sun, and Barnard's star are red dwarfs. They're faint, small, and will live for trillions of years. The Sun, with a surface temperature of about 5,700 Kelvin, falls in the middle. It emits light across the entire visible spectrum, but peaks in the green-yellow range. Our eyes perceive this as white, though we often call the Sun yellow because of how its light appears when scattered by Earth's atmosphere. But color is just the beginning. When starlight is passed through a spectrograph, a device that splits light into its component wavelengths, it reveals a spectrum, a rainbow of colors crossed by dark lines. These lines are called absorption lines, and they're caused by elements in the star's outer layers absorbing specific wavelengths of light. Each element absorbs light at specific wavelengths, creating a unique pattern of lines. Hydrogen produces a set of lines called the Balmer series. Calcium produces two strong lines in the violet part of the spectrum. Iron produces hundreds of lines across the visible and ultraviolet range. By studying these lines, astronomers can determine what a star is made of. The Sun, for example, is about 73% hydrogen, 25% helium, and 2% heavier elements like carbon, oxygen, nitrogen, and iron. This composition is typical for a star of the Sun's age and type. But the spectrum reveals more than just composition. The width of the absorption lines can indicate the star's rotation rate and surface gravity. The overall shape of the spectrum can reveal the star's temperature and luminosity. And if the lines are shifted toward the red or blue end of the spectrum, that indicates the star is moving away from or toward us, a phenomenon called the Doppler shift. The Doppler shift is how we measure the motion of stars. If a star is moving away from Earth, its light is stretched to longer wavelengths, shifted toward the red. If it's moving toward Earth, its light is compressed to shorter wavelengths, shifted toward the blue. By measuring this shift, astronomers can calculate the star's velocity along our line of sight. This technique has been used to discover thousands of exoplanets. When a planet orbits a star, it causes the star to wobble slightly, moving toward and away from us in a regular pattern. This wobble creates a periodic Doppler shift in the star's spectrum, and by measuring that shift, astronomers can infer the presence of a planet, estimate its mass, and determine its orbital period. Starlight also reveals a star's age, though more indirectly. Young stars are often found in clusters, surrounded by the gas and dust from which they formed. They may still be accreting material, and they often have strong stellar winds and high rotation rates. Old stars have used up much of their hydrogen fuel, and their spectra show higher abundances of heavier elements because they formed from gas that had been enriched by earlier generations of stars. The Sun is middle-aged, about 4.6 billion years old, roughly halfway through its main sequence lifetime. Its spectrum shows the characteristic absorption lines of hydrogen, helium, calcium, iron, and other elements, and the strength and shape of these lines match theoretical models of a star with the Sun's mass and age. What's remarkable is how much we can learn from light alone. We've never sent a probe to another star. We've never collected a sample of stellar material. We've never measured a star's temperature or composition directly. And yet, we know these things with extraordinary precision because the light tells us. Every photon that reaches Earth from a distant star carries information encoded in its wavelength, its intensity, its polarization. That information has traveled across space, sometimes for thousands or millions of years, and when it reaches a telescope, it can be decoded, revealing the star's secrets. And this works for every star. The nearest stars, like Proxima Centauri, 4.2 light-years away. The brightest stars, like Sirius, 8.6 light-years away. The faintest stars, red dwarfs so dim they require powerful telescopes to detect. And even stars in other galaxies, millions or billions of light-years distant. The light from those distant stars left them long before humans existed. Some of it left before the Earth existed. Some of it left before the Sun existed. And yet, when it reaches us, we can still read it, still learn from it, still use it to understand the universe. Starlight is patient. It travels for eons, carrying information, waiting to be seen. And when it finally reaches an eye, or a telescope, or a detector, it delivers its message, unchanged by the journey. That light is still traveling, right now, from stars in every direction. Some of it will reach Earth tomorrow. Some of it will reach Earth in 1,000 years. Some of it will never reach Earth at all, because the universe is expanding, and those stars are too far away, their light red-shifted beyond detection. But the light from nearby stars, our neighbors in the galaxy, that light is here now, constant and reliable, a stream of information that has been flowing for billions of years and will continue flowing for billions more. And all we have to do is look up. The most common stars in the universe are also the least dramatic. They're called red dwarfs, and they make up roughly 70 to 80% of all stars in the Milky Way. They're small, cool, dim, and extraordinarily long-lived. A red dwarf born today will still be shining, essentially unchanged, trillions of years from now, long after the sun has exhausted its fuel and faded away. Red dwarfs are defined as stars with masses between about 0.075 and 0.5 times the mass of the Sun. Below 0.075 solar masses, an object doesn't have enough gravity to sustain hydrogen fusion and it becomes a brown dwarf instead. A failed star that glows faintly from residual heat but never ignites. A typical red dwarf has a mass of around 0.2 solar masses, a radius of about 0.3 solar radii, and a surface temperature between 2500 and 4000 Kelvin. This gives them a deep red or orange color and makes them incredibly faint. The nearest red dwarf, Proxima Centauri, is only 4.2 light-years away, but it's far too dim to see with the naked eye. You need a telescope. Despite their faintness, red dwarfs are incredibly efficient. They fuse hydrogen very slowly because their cores are cooler and less dense than those of larger stars. But this slow burn means they can run for an extraordinarily long time. A red dwarf with a mass of 0.1 solar masses can shine for 10 trillion years. That's 1,000 times longer than the current age of the universe. To put that in perspective, the universe is about 13.8 billion years old. The sun will live for about 10 billion years. A small red dwarf will live for 10 trillion years. That's 10,000 billion. 10 million million. No red dwarf has ever died of old age. None ever will, for trillions of years. Every red dwarf that has ever formed is still shining, still fusing hydrogen, still in its infancy. This longevity has interesting implications. Red dwarfs are stable. They don't swell into giants. They don't explode as supernovae. They don't undergo dramatic changes. They simply burn steadily, dimly, quietly for eons. Some red dwarfs also have planets. The TRAPPIST-1 system, about 40 light-years from Earth, is a red dwarf with at least 7 known planets, several of which are in the habitable zone. Proxima Centauri has at least 2 planets, one of which, Proxima Centauri b, orbits within the habitable zone. Life on a planet orbiting a red dwarf would experience a very different kind of star. Red dwarfs are much dimmer than the Sun, so the habitable zone is much closer to the star. Proxima Centauri b orbits its star at a distance of about 0.05 astronomical units, about 1/20th the distance between Earth and the Sun. At that distance, the planet is likely tidally locked, meaning one side always faces the star and the other side is always in darkness. The star would appear much larger in the sky than the Sun does from Earth, and the light would be deep red or orange because that's the color a red dwarf emits most strongly. Photosynthesis, if it occurred, might rely on different wavelengths than it does on Earth, absorbing red and infrared light instead of blue and red. Red dwarfs also have some challenges for habitability. Many are flare stars, meaning they experience sudden, intense bursts of radiation that could strip away a planet's atmosphere over time. Their habitable zones are so close to the star that planets there receive intense stellar wind. And because planets in the habitable zone are likely tidally locked, they would have extreme temperature differences between day and night sides unless their atmospheres could redistribute heat effectively. But despite these challenges, red dwarfs offer something no other star can: time. Billions upon billions of years for life to develop, adapt, and evolve. Trillions of years for civilizations to rise and explore. The Sun will burn out in 5 billion years. A red dwarf will still be shining 1,000 times longer than that. And there are so many of them. In the solar neighborhood, the region of space within about 30 light-years of Earth, roughly 70% of all stars are red dwarfs. Many of them have planets. Some of those planets are likely rocky, temperate, and capable of supporting liquid water on their surfaces. We don't yet know if any of these planets host life, but the sheer number of red dwarfs, combined with their longevity and stability, makes them prime candidates for long-term habitability. If life exists elsewhere in the galaxy, there's a good chance it evolved on a planet orbiting a red dwarf. And those stars will keep shining, hosting those planets, providing warmth and light for longer than almost anything else in the universe. They are the marathon runners of the cosmos, slow and steady, outlasting the sprinters by factors of thousands or millions. When the Sun exhausts its hydrogen and swells into a red giant, red dwarfs will still be burning. When the Sun sheds its outer layers and becomes a white dwarf, slowly cooling over billions of years, red dwarfs will still be burning. When galaxies collide and merge, when the Milky Way and Andromeda become one, red dwarfs will still be burning. And even in the unimaginably distant future, when the universe has expanded so much that galaxies can no longer see each other, when star formation has ceased because all the gas has been used up, when most stars have died, red dwarfs will still be there, tiny embers glowing faintly in the dark, the last lights left on in an otherwise darkening cosmos. There is something deeply calming about that. Red dwarfs are not grand, they are not spectacular, but they endure, they persist, they outlast everything. And right now, somewhere within 20 light-years of where you are, a red dwarf is shining just as it has been for billions of years, just as it will continue to do for trillions more. It doesn't know you exist, it doesn't care, it simply shines. And that's enough. Most stars are not alone. In fact, it's estimated that more than half of all stars exist in binary or multiple star systems, gravitationally bound to one or more companions orbiting a common center of mass. These systems are not chaotic. They're remarkably stable, governed by the same laws of gravity that keep planets in orbit around stars. A binary star system consists of two stars orbiting each other. The stars may be similar in mass, or one may be much larger than the other. They may orbit close together, completing an orbit in days or hours, or they may be separated by thousands of astronomical units, taking hundreds of thousands of years to complete one orbit. The closest binary systems are called contact binaries, where the two stars are so close their outer layers touch or even merge. These systems are rare, but they demonstrate just how tightly gravity can bind objects together. In some cases, material flows from one star to the other, creating complex interactions that can lead to novae or other energetic events. But most binary systems are far more sedate. The two stars orbit at a comfortable distance, neither disturbing the other, each shining steadily on its own. If planets exist in such a system, they might orbit both stars, a circumbinary orbit, or they might orbit just one star, far enough from the other that its gravity doesn't interfere. The Alpha Centauri system, the closest star system to the Sun, is a triple star system. It consists of Alpha Centauri A and Alpha Centauri B, two Sun-like stars that orbit each other every 80 years, and Proxima Centauri, a red dwarf that orbits the pair at a much greater distance. The entire system is only 4.37 light-years from Earth, and it's been studied extensively because of its proximity. From a planet orbiting Alpha Centauri A, the sky would contain two suns. One would be similar in brightness to the Sun as seen from Earth. The other would be slightly dimmer, but still brilliant, a luminous point moving across the sky in a years-long arc. The light from these two stars would overlap, creating complex shadows and brighter-than-Earth daytime illumination. Binary systems are common throughout the galaxy. Sirius, the brightest star in the night sky, is a binary system. Sirius A is a bright, hot, white main sequence star. Sirius B is a white dwarf, the remnant core of a star that exhausted its fuel and shed its outer layers billions of years ago. The two stars orbit each other every 50 years. Algol in the constellation Perseus is another well-known binary system. It's an eclipsing binary, meaning the two stars pass in front of each other as seen from Earth, causing the system's brightness to vary in a regular pattern. Every 2.87 days, the dimmer star passes in front of the brighter one, and Algol's brightness drops noticeably for several hours. This variability was noted by ancient astronomers, and Algol became known as the demon star because its changing brightness was considered ominous. But there's nothing ominous about it. It's just geometry. Two stars orbiting, one occasionally blocking the light of the other, as regular and predictable as clockwork. Binary systems also provide some of the most precise measurements in astronomy. By observing how the stars orbit each other, astronomers can calculate their masses because the orbital period and separation depend on the combined mass of the system. This technique has been used to measure the masses of hundreds of stars, providing crucial data for testing theoretical models of stellar structure. Some binary systems are so close together that they exchange mass. If one star expands into a red giant, its outer layers can spill onto its companion, creating an accretion disk and sometimes triggering a nova, a sudden brightening caused by nuclear fusion igniting on the surface of the accreting star. These systems are dynamic, but they're not unstable. The mass transfer happens gradually over thousands or millions of years. Multiple star systems, systems with 3 or more stars, are also surprisingly common. They're more complex because the gravitational interactions between 3 or more bodies can become chaotic over long timescales. But many of these systems are hierarchical, meaning the stars group into pairs that orbit each other, with the pairs themselves orbiting at much greater distances. This arrangement keeps the system stable. Castor, one of the 2 bright stars in the constellation Gemini, is actually a sextuple star system. It consists of 3 binary pairs, all gravitationally bound and orbiting a common center of mass. From a distance, Castor looks like a single point of light, but through a telescope, it resolves into multiple stars. And with spectroscopy, astronomers have identified 6 distinct stellar components. These systems are not rare exceptions, they're the norm. Most stars have companions. Most stars are part of a larger system, dancing through space in slow, predictable orbits. There's something calming about that too. Stars are not isolated. They're not alone. They exist in relationships, bound together by gravity, moving together through the galaxy. And these relationships last. Binary stars that formed together billions of years ago are still orbiting each other, still influencing each other, still bound by the same forces that brought them together in the first place. The orbits are stable. The motion is predictable. The system persists, and will continue to persist for billions of years more. When you look at a star, you're looking back in time. The light you see left that star years, decades, centuries, or even millennia ago, and has been traveling through space ever since, moving at the speed of light, covering about 300,000 kilometers every second until it finally reaches your eyes. This means that the stars you see are not as they are now. They're as they were when their light began its journey. You're seeing the past, preserved in photons. The nearest star, Proxima Centauri, is 4.2 light-years away. The light you see from Proxima Centauri tonight left the star 4.2 years ago, in the year 2021. If Proxima Centauri exploded right now, you wouldn't know for 4.2 years. The star would still appear in the sky, unchanged, until the light from the explosion finally arrived. Sirius, the brightest star in the night sky, is 18.6 light-years away. The light you see from Sirius left in the year 2017. Vega, the 5th brightest star, is 25 light-years away. Its light left in the year 2001. Betelgeuse, the red supergiant in Orion's shoulder, is about 550 light-years away. The light you see from Betelgeuse left Earth in the year 1476, during the Renaissance, when Leonardo da Vinci was 24 years old. And the most distant stars visible to the naked eye are several thousand light-years away, meaning their light has been traveling since before the rise of ancient civilizations, crossing the galaxy while humans invented writing, built cities, and developed science. But stars aren't the only sources of ancient light. When you look at the Andromeda Galaxy, visible as a faint smudge in the night sky, you're seeing light that left 2.5 million years ago. That light began its journey during the Pliocene epoch, when early human ancestors were just beginning to use stone tools. The light from more distant galaxies is even older. The Hubble Space Telescope has captured images of galaxies whose light has been traveling for over 13 billion years, light that left those galaxies when the universe was less than 1 billion years old, long before the Sun or Earth existed. This is one of the most extraordinary things about astronomy. It's the study of the past. We can't see distant objects as they are now. We can only see them as they were when their light began its journey toward us. And because the universe is so vast, this delay is significant. Light from the nearest stars takes years to reach us. Light from nearby galaxies takes millions of years. Light from the most distant galaxies takes billions of years. This also means that when we observe the universe, we're seeing it at different ages simultaneously. The Sun as it was 8 minutes ago, Proxima Centauri as it was 4 years ago, Betelgeuse as it was 5 centuries ago, Andromeda as it was 2.5 million years ago, distant galaxies as they were billions of years ago. The universe is a patchwork of past moments, all arriving at Earth at the same time, assembled into a single view that spans cosmic history. And those photons, the particles of light that carry this information, are incredibly durable. They don't decay, they don't degrade, they just travel. A photon emitted from a star 10,000 years ago is identical to a photon emitted yesterday. The journey doesn't wear it out. What's also remarkable is that light travels in straight lines, at a constant speed, regardless of the motion of its source. This constancy is what makes the speed of light useful as a measuring stick. When we say a star is 10 light-years away, we mean its light takes 10 years to reach us, traveling at 300,000 kilometers per second. This also means that light from very distant objects is redshifted by the expansion of the universe. As space itself expands, the wavelength of light traveling through it is stretched, shifting it toward the red end of the spectrum. The farther away an object is, the faster space is expanding between us and it, and the more its light is redshifted. This redshift is how we know the universe is expanding. By measuring the redshift of distant galaxies and comparing it to their distance, astronomers have determined that the universe has been expanding for about 13.8 billion years, ever since the Big Bang. But even with this expansion, light endures. Photons emitted from the first stars, over 13 billion years ago, have traveled across the expanding universe and are still reaching us today. We can detect them with powerful telescopes, and when we do, we're seeing the universe as it was in its infancy. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, is even older. That light has been traveling for over 13.7 billion years. It's the oldest light in the universe, and it's everywhere, filling space with a nearly uniform glow at a temperature of about 2.7 Kelvin. Every photon in the cosmic microwave background is a relic from the early universe, a messenger from a time before stars, before galaxies, before anything we recognize. And those photons are still here, still traveling, still carrying information. Light is patient, it doesn't stop, it doesn't turn around. It just moves at the maximum speed allowed by the laws of physics, crossing unimaginable distances until it encounters something, a planet, a detector, an eye. And when it does, it delivers its message, unchanged by the journey. Right now, photons are arriving at Earth from stars thousands of light-years away. Some of those photons began their journey before human civilization existed. Some began their journey before modern humans existed. And yet they arrive now, indistinguishable from photons emitted yesterday, carrying the same information, revealing the same truths. The stars you see tonight are ghosts, in a sense, images of the past preserved in light, but they're also real, tangible connections to distant objects, proof that the universe is vast but knowable, ancient but observable. And every night, more light arrives. More photons complete their long journeys. More information reaches us from the cosmos. The stars shine, the light travels, and we look up and see. At the core of every star, something extraordinary is happening. Hydrogen nuclei, protons, are colliding with such energy that they overcome the electromagnetic force that normally keeps them apart, and they fuse together, forming helium. In the process, A tiny amount of mass is converted into energy, released as gamma-ray photons that begin a long journey outward. This process, called nuclear fusion, is what powers stars. It's the reason they shine, the reason they're hot, the reason they exist at all. And it's remarkably gentle. Fusion doesn't happen suddenly. It doesn't happen all at once. It happens one collision at a time, deep in the core, where temperatures reach millions of degrees and pressures are millions of times greater than atmospheric pressure on Earth. In the Sun's core, the temperature is about 15 million Kelvin. At that temperature, hydrogen nuclei move at speeds of hundreds of kilometers per second. When they collide, they sometimes get close enough that the strong nuclear force, the fundamental force that binds protons and neutrons together, overcomes the electromagnetic repulsion between them, and they fuse. But sometimes is key. Most collisions don't result in fusion. The nuclei bounce off each other and continue moving. Fusion is rare, even in the core of the Sun. Any given proton might wait billions of years before fusing with another proton. And yet, because there are so many protons in the Sun's core, an almost incomprehensible number, fusion is happening constantly. About 600 million tons of hydrogen are fused into helium every second in the Sun. That sounds like a lot, but the Sun contains 2 × 10⁻30 kilograms of hydrogen. At this rate, it has enough fuel for another 5 billion years. The fusion process in stars like the Sun follows a pathway called the proton-proton chain. It begins when 2 protons collide and fuse, forming a deuterium nucleus, a proton and a neutron bound together. This step is the slowest because it requires one of the protons to convert into a neutron via the weak nuclear force, releasing a positron and a neutrino in the process. Once deuterium is formed, the next steps are faster. The deuterium nucleus fuses with another proton, forming helium-3. Then 2 helium-3 nuclei collide and fuse, forming helium-4 and releasing 2 protons back into the mix. The net result, 4 protons go in, 1 helium-4 nucleus comes out, along with 2 positrons, 2 neutrinos, and several gamma-ray photons. The mass of the helium nucleus is slightly less than the combined mass of the 4 protons, and that missing mass has been converted into energy. This energy is what keeps the Sun shining. The gamma-ray photons scatter through the dense core, getting absorbed and re-emitted countless times, gradually losing energy and shifting toward longer wavelengths. By the time they reach the surface, they've become visible light photons, the light we see. In more massive stars, fusion can proceed via a different pathway called the CNZ cycle, which uses carbon, nitrogen, and oxygen as catalysts. The end result is the same. Hydrogen fuses into helium and energy is released, but the CNO cycle dominates in stars hotter than the Sun. What's important to understand is that fusion is not an explosion. It's a controlled, steady reaction, regulated by the balance between gravity and pressure. If the core gets too hot, pressure increases, pushing outward and causing the core to expand slightly. This cools the core, slowing fusion. If the core gets too cool, pressure decreases, allowing gravity to compress the core, heating it up and speeding up fusion. This self-regulating mechanism keeps stars stable. It's why the Sun has been shining steadily for 4.6 billion years. It's why main sequence stars can exist for billions or even trillions of years without running away or collapsing. Fusion is also clean. It doesn't produce pollution, it doesn't produce radioactive waste, at least not in the dangerous sense. The helium produced by fusion is stable and non-reactive. The neutrinos produced escape the star almost immediately, carrying away some energy but otherwise interacting with nothing. The photons produced eventually reach the surface and radiate into space as light. And fusion is efficient. The amount of energy released by fusing 1 kilogram of hydrogen into helium is about 6 times 10 to the 14th joules. That's enough energy to power a large city for days. The Sun fuses 600 million tons per second, releasing about 3.8 times 10 to the 26th watts of power. That's 3.8 followed by 26 zeros, an almost unimaginable amount of energy. And yet, from our perspective on Earth, 93 million miles away, that energy feels gentle. It warms the surface, it powers photosynthesis, it drives weather patterns, it lights the day. The Sun doesn't burn us, it doesn't destroy us. It simply provides energy, steadily, reliably, in amounts that are perfectly suited for life. This is one of the great fortunes of our existence. The Sun is not too hot, not too cold, not too bright, not too dim. It's exactly the right kind of star, at exactly the right distance, providing exactly the right amount of energy. And it will continue doing so for billions of years. Fusion is the engine. Gravity is the container. Pressure is the regulator. Together, they create a system so stable, so long-lasting, that it outlasts continents, outlasts species, outlasts epochs. The Sun has been fusing hydrogen for longer than life has existed on Earth. It will continue fusing hydrogen long after humans are gone. And somewhere in the core, right now, a proton is colliding with another proton, fusing into deuterium, releasing energy, contributing to the light that will eventually reach Earth 8 minutes from now. It's happening constantly, quietly, inevitably. And it's been happening for 4.6 billion years. Stars do not last forever. Eventually they exhaust their fuel, and when they do, they change. But even in death, stars follow predictable paths, governed by the same laws of physics that shape their lives. The fate of a star depends almost entirely on its mass. Low-mass stars end quietly. High-mass stars end dramatically. But in both cases, the process is well understood, the timeline is calculable, and the outcome is certain. For a star like the Sun, the end begins about 5 billion years from now, when the hydrogen in the core is finally exhausted. At that point, fusion stops, and without the outward pressure from fusion, gravity begins to compress the core. This compression heats the core, and eventually, a shell of hydrogen surrounding the core becomes hot enough to fuse. This shell fusion releases energy, but it also causes the star's outer layers to expand. The star grows larger, cooler, and redder, becoming a red giant. The Sun will swell to perhaps 50 or 100 times its current radius, large enough to engulf Mercury and Venus. Earth may survive, but it will be scorched, its atmosphere stripped away, its surface turned to molten rock. The red giant phase lasts for about 1 billion years. During this time, the core continues to contract, heating up until it reaches 100 million Kelvin, hot enough for helium to fuse into carbon and oxygen. This is called the helium flash, and it marks the beginning of the horizontal branch phase, where the star fuses helium in its core and hydrogen in a surrounding shell. This phase is shorter, lasting only a few 100 million years. When the helium in the core is exhausted, the core contracts again, and the star enters the asymptotic giant branch phase, where it fuses helium and hydrogen in separate shells. The star becomes even larger and more luminous, but also more unstable. It begins to pulsate, shedding its outer layers in slow, gentle waves. These waves form a planetary nebula, a glowing shell of gas surrounding the star's core. The core itself, no longer producing energy, cools and contracts until electron degeneracy pressure, a quantum mechanical effect, halts the collapse. The core becomes a white dwarf, a dense, Earth-sized object composed mostly of carbon and oxygen, with a surface temperature of tens of thousands of Kelvin. The white dwarf doesn't fuse anything. It simply radiates away its residual heat, gradually cooling over billions of years. Eventually, after tens or hundreds of billions of years, it will cool enough to become a black dwarf, a cold, dark, inert lump of matter that no longer emits visible light. No black dwarfs exist yet. The universe isn't old enough. Every white dwarf that has ever formed is still glowing, still radiating heat, still visible. For more massive stars, those with more than about 8 solar masses, the end is more dramatic. These stars fuse hydrogen, then helium, then carbon, oxygen, neon, magnesium, silicon, and finally iron. Each stage happens faster than the last. Hydrogen fusion lasts millions of years. Iron fusion, if it could occur, would last less than a day. But iron doesn't fuse. Fusing iron consumes energy instead of releasing it. So when a massive star's core becomes iron, fusion stops. The core collapses in less than a second, and the collapse releases so much gravitational energy that it drives a supernova, an explosion that briefly outshines entire galaxies. The core itself becomes a neutron star, an object about 20 kilometers across, but with a mass greater than the Sun's, held up by neutron degeneracy pressure. If the core is massive enough, even neutron degeneracy pressure can't stop the collapse, and it becomes a black hole, a region of space where gravity is so strong that not even light can escape. The supernova explosion scatters heavy elements, carbon, oxygen, iron, gold, into space, enriching the interstellar medium and seeding future generations of stars and planets. The Sun, the Earth, and everything on it, including you, are made from elements forged in the cores of stars that exploded billions of years ago. What's remarkable about all of this is how predictable it is. Given a star's mass, composition, and age, astronomers can calculate its future with extraordinary precision. They know when it will leave the main sequence. They know how large it will become as a red giant. They know whether it will end as a white dwarf, a neutron star, or a black hole. This predictability is one of the triumphs of astrophysics. Stars are complex systems, but they follow rules. And those rules allow us to understand not just what stars are, but what they will become. The Sun will become a red giant in about 5 billion years. Betelgeuse, the red supergiant in Orion, could explode as a supernova any time in the next 100,000 years, or it may have already exploded, and we won't know until the light reaches us. Sirius B, the white dwarf companion to Sirius A, will continue cooling for tens of billions of years, gradually fading until it's no longer visible. And, throughout the galaxy, stars are ending their lives right now. Some are swelling into red giants, shedding their outer layers into space. Some are exploding as supernovae, scattering their remains across light years. Some are cooling as white dwarfs, slowly dimming over eons. But most stars, the vast majority, are still on the main sequence, fusing hydrogen, shining steadily, with billions or trillions of years left to live. The universe is not in a hurry. Stars live for so long that even their deaths are slow, measured in millions or billions of years. A red giant phase lasting 1 billion years. A white dwarf cooling for 10 billion years. A neutron star spinning for trillions of years, gradually slowing but never stopping. Even in death, stars are patient, and the elements they produce, the energy they release, the structures they leave behind, all of it continues. The remnants of dead stars become the building blocks of new stars, new planets, new systems. The cycle continues. And will continue, for as long as there is gas to form stars, for as long as stars have fuel to burn. That's a very, very long time. Space is not crowded. It's almost entirely empty. The distances between stars are so vast that even traveling at the speed of light, it would take years to reach the nearest star, decades to reach more distant stars, and centuries or millennia to cross the galaxy. This emptiness is hard to grasp because our experience is shaped by Earth, where distances are measured in meters or kilometers, and travel times are measured in hours or days. But in space, the scales are different. Distances are measured in light years, and travel times, at least for anything moving slower than light, are measured in millennia. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. In more familiar units, that's about 40 trillion kilometers or 25 trillion miles. If you could drive to Proxima Centauri at highway speeds, about 100 kilometers per hour, it would take 45 million years. The fastest spacecraft ever built, the Parker Solar Probe, travels at about 200 kilometers per second at its closest approach to the Sun. At that speed, it would still take more than 6,600 years to reach Proxima Centauri. No human-made object has ever traveled to another star. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object, about 24 billion kilometers from Earth. That sounds like a lot, but it's only 0.0025 light-years. At its current speed, Voyager 1 would take about 70,000 years to reach Proxima Centauri, if it were heading in that direction. It's not. These distances are so large that they make interstellar travel, at least with current technology, effectively impossible. Even at a significant fraction of the speed of light, say 10%, it would take 42 years to reach Proxima Centauri, and accelerating a spacecraft to 10% of the speed of light would require enormous amounts of energy far beyond what we can currently produce. But this emptiness is also what makes the universe calm. Stars are not colliding. Planets are not crashing into each other. The galaxy is not chaotic. It's orderly, with each star moving through space on a predictable orbit, separated from its neighbors by distances so large that close encounters are incredibly rare. The Sun, for example, moves through the galaxy at about 250 kilometers per second. It completes one orbit around the galactic center every 230 million years. During that time, it passes by thousands of other stars, but none of them come close enough to disturb the solar system. The nearest approach is typically measured in light years, and at those distances, gravitational interactions are negligible. Stellar collisions do happen, but they're extraordinarily rare in the main disk of the galaxy. In dense regions, like the cores of globular clusters, where stars are packed much more tightly together, collisions are more common. But even there, the timescale between collisions is measured in millions or billions of years. In the solar neighborhood, the average distance between stars is about 5 light-years. In a sphere of that radius, you'd expect to find, on average, one star, sometimes none, sometimes a few. The density of stars in the galaxy varies, but on average, there's about one star per 300 cubic light-years. This means that space is almost entirely empty. If you were to pick a random point in the galaxy, the chances are overwhelming that you'd be light-years away from the nearest star, floating in the cold, dark vacuum of interstellar space. But even this empty space isn't truly empty. It contains the interstellar medium, a thin gas of hydrogen and helium, along with trace amounts of heavier elements and dust. The density of this gas is incredibly low, typically around 1 atom per cubic centimeter. For comparison, the air you're breathing contains about 30 quintillion molecules per cubic centimeter. That's 30 billion billion. But even at such low densities, the interstellar medium adds up. There's so much space between stars that the total mass of the interstellar medium in the Milky Way is about 10 billion times the mass of the Sun, roughly 10 to 15% of the galaxy's total visible mass. This gas is where new stars form. Over millions of years, it can clump together, collapse under its own gravity, and give birth to protostars. And when stars die, they return their material to the interstellar medium, enriching it with heavier elements that will eventually be incorporated into the next generation of stars and planets. The emptiness of space also means that travel between stars, if it were possible, would be remarkably uneventful. You wouldn't need to dodge asteroids or navigate through debris fields, as depicted in science fiction. You'd simply move through the void with nothing to see but the distant stars in every direction, unchanging for years or decades or centuries. This emptiness is not lonely though. It's peaceful. It's a reminder that the universe is not crowded, not rushed, not frantic. It's vast and calm and patient. And the stars, separated by these enormous distances, shine quietly, influencing each other only slightly, mostly just existing, moving through space on their long, slow orbits. The Sun will complete about 20 more orbits around the galaxy before it exhausts its hydrogen and becomes a red giant. During that time, it will pass by tens of thousands of other stars, but none of them will come close enough to matter. The galaxy is stable. The stars are safe. The distances between them ensure that. And that's calming, in a way. The universe is not fragile. It's not about to fall apart. It's held together by gravity, organized by motion, separated by distance into a structure that is both vast and orderly. You can look up at the stars and know that they'll still be there tomorrow, and the next day, and 1,000 years from now, and 1,000,000 years from now. They're separated by distances too large to easily comprehend. But those distances are what keep them stable, what keep them shining, what make the universe a place where stars can exist for billions of years without interference. The emptiness is not a flaw, it's a feature. And it's everywhere, surrounding every star, filling every gap, reminding us that the universe is far larger than we can ever truly grasp, but also far calmer than we might imagine. In certain regions of the galaxy, where gas and dust have accumulated in particularly dense clouds, stars are being born right now. These regions are called stellar nurseries, and they're some of the most beautiful and scientifically important structures in the galaxy. The most famous stellar nursery is the Orion Nebula, located about 1,300 light-years from Earth in the constellation Orion. It's visible to the naked eye as a fuzzy patch of light in Orion's sword just below the 3 stars that form the belt. Through a telescope, the nebula reveals intricate structures, glowing gas, dark dust lanes, and embedded young stars still surrounded by the remnants of the clouds from which they formed. The Orion Nebula is relatively close and very active. It contains thousands of young stars, many of them less than 1,000,000 years old. Some are still protostars, not yet hot enough to sustain hydrogen fusion. Others are on the main sequence, shining brightly and ionizing the surrounding gas, causing it to glow. The nebula itself is about 24 light-years across, and it's part of a much larger structure called the Orion Molecular Cloud Complex, which spans hundreds of light-years and contains enough material to form hundreds of thousands of stars. Star formation in these regions happens slowly. A dense clump of gas begins to collapse under its own gravity. Over hundreds of thousands of years, it contracts, heats up, and eventually forms a protostar. The protostar continues to accrete material from the surrounding cloud, growing in mass until it becomes hot enough to begin fusion. This process is not instantaneous. A protostar might spend 1,000,000 years accreting material before it reaches the main sequence. During that time, it's surrounded by a disk of gas and dust, the same kind of disk from which planets can form. The protostar is also often obscured by the surrounding cloud, making it invisible in optical light, but bright in infrared wavelengths which can penetrate the dust. The Hubble Space Telescope has captured remarkable images of protostars in the Orion Nebula, showing them surrounded by glowing disks and jets of material being ejected along their rotation axes. These jets, called Herbig-Haro objects, are created when material falling onto the protostar is redirected outward at high speeds, creating shock waves that heat and illuminate the surrounding gas. Other famous stellar nurseries include the Eagle Nebula, home to the Pillars of Creation, towering columns of gas and dust, where new stars are forming. The pillars are sculpted by intense ultraviolet radiation from nearby massive stars, which evaporates the outer layers of the clouds while denser regions inside remain intact, continuing to collapse and form stars. The Carina Nebula, about 7,500 light-years away, is another spectacular region of star formation. It contains some of the most massive and luminous stars known, including Eta Carinae, a hypergiant star system that underwent a massive eruption in the 1840s and is expected to explode as a supernova sometime in the relatively near future, though near in astronomical terms could still mean thousands or even hundreds of thousands of years. These stellar nurseries are not static. They're constantly evolving. Young stars heat and ionize the gas around them, creating expanding bubbles of hot plasma. The most massive stars have strong stellar winds that push gas away, compressing surrounding material and, potentially, triggering the formation of new stars. And when massive stars finally explode as supernovae, the shock waves compress nearby clouds, seeding more star formation. This cycle of birth, life, and death has been running for billions of years in the Milky Way and in every galaxy in the universe. Stars form from gas clouds, live for millions or billions of years, then die and return their material to the interstellar medium, where it can eventually form new stars. The gas from which the Sun formed 4.6 billion years ago was enriched with heavy elements from earlier generations of stars. The Sun itself contains about 2% heavier elements, everything other than hydrogen and helium, elements that were forged in the cores and explosions of stars that lived and died before the solar system existed. And when the Sun dies, billions of years from now, it will shed its outer layers into space, contributing carbon and oxygen to the interstellar medium. That material will drift through space, perhaps for millions of years, until it's swept up by a collapsing cloud and incorporated into a new star or a new planet, or perhaps something we can't yet imagine. This recycling of material is one of the fundamental processes in the universe. Nothing is permanent. Everything is reused. The atoms in your body have been part of countless structures over the history of the universe. Gas clouds, stars, planets, asteroids, comets, perhaps even other living beings on other worlds. But the process happens slowly. A gas cloud might drift through space for hundreds of millions of years before collapsing to form a star. That star might shine for billions of years. When it dies, its remnants might drift for millions more years before being incorporated into something new. There's no rush. The universe has time. Vast, almost incomprehensible amounts of time. And throughout all of that time, in stellar nurseries scattered across every galaxy, new stars are being born, quietly, slowly, inevitably. The Orion Nebula will continue forming stars for millions of years. The gas will gradually be used up or dispersed, and eventually the nebula will fade, leaving behind a cluster of young stars that will gradually drift apart as they orbit the galaxy. But by then, Other clouds will have collapsed, other nurseries will have formed, and the process will continue. Star formation is not rare. It's happening right now in the Milky Way, at a rate of about 1 to 3 solar masses per year. That means that every year, enough material to form 1 to 3 sun-like stars is collapsing into protostars somewhere in the galaxy. Multiply that by the roughly 2 trillion galaxies in the observable universe, and star formation becomes a truly staggering phenomenon. Billions of new stars are born every year across the cosmos. And yet, from our perspective, it seems rare because the galaxy is so large and the nurseries are so far apart. We can only see the nearest ones, the Orion Nebula, the Eagle Nebula, the Carina Nebula, and even those are hundreds or thousands of light years away. But they're there, glowing softly in infrared light, hidden behind veils of dust, slowly collapsing, heating up, forming stars. And those stars, once born, will shine for billions of years. They'll become the lights in someone else's sky. They'll warm planets. They'll perhaps give rise to life. And all of it begins in these quiet, dark, cold clouds, where gravity slowly, patiently, inevitably pulls matter together. The process is ancient. It's been happening since the first stars formed, over 13 billion years ago. And it will continue happening for trillions of years more until the last gas clouds collapse, the last stars ignite, and the era of star formation finally ends. But that's so far in the future that it's nearly meaningless. For now, and for a very long now, stars are being born. And that's something quietly comforting. The universe is not running out. It's not winding down. Not yet. It's still creating, still forming new structures, still bringing new lights into existence. And those lights will shine, steadily and calmly, for billions of years. If you've ever looked at a star and seen it twinkling, flickering, changing in brightness, you've witnessed not a property of the star itself, but an effect of Earth's atmosphere. Stars don't flicker. They shine with remarkable constancy, emitting light at a steady rate determined by the balance of forces in their interiors. The twinkling we see is caused by atmospheric turbulence. Light from a star travels through space for years, decades, or centuries, moving in a perfectly straight line at a constant speed. But when it reaches Earth's atmosphere, it encounters pockets of air at different temperatures and densities. These pockets bend and scatter the light slightly, causing the star's apparent position and brightness to fluctuate. This is why stars twinkle more. When they're near the horizon, the light has to travel through more atmosphere to reach your eyes, and why they twinkle less when they're high overhead, where the light path through the atmosphere is shorter. But if you could observe stars from space, above the atmosphere, they wouldn't twinkle at all. They'd be steady, constant points of light, unchanging from moment to moment. This constancy is one of the defining characteristics of stars. Unlike lightning, which flashes once and disappears, or fire, which flickers and varies, stars shine steadily. The sun has been producing light at essentially the same rate for billions of years. Its total energy output varies by less than 0.1% over its 11-year solar cycle. Other stars are even more stable. Red dwarfs can shine for tens of billions or hundreds of billions of years with almost no variation in brightness. Their fusion rates are so slow and so steady that they're effectively unchanging over timescales, longer than the current age of the universe. Some stars do vary in brightness, but these are the exceptions, and even they follow predictable patterns. Cepheid variables, for example, are stars that periodically expand and contract, causing their brightness to rise and fall in a regular cycle. The period of this cycle is directly related to the star's intrinsic luminosity, which makes Cepheids incredibly useful for measuring cosmic distances. But even Cepheids aren't truly unstable. They're just pulsating in a predictable way, driven by a mechanism called the Kappa mechanism, where helium in the star's outer layers becomes ionized and opaque when the star contracts, trapping heat and causing it to expand, then becoming transparent again when the star expands, allowing heat to escape and causing it to contract. The cycle repeats, and the star's brightness varies, but the variation itself is regular and predictable. Eclipsing binaries also vary in brightness, but only because one star periodically passes in front of the other, blocking some of its light. The stars themselves are shining steadily. We just see less of their combined light during eclipses. True stellar instability, where a star's energy output fluctuates unpredictably, is rare and usually associated with the late stages of stellar evolution. Red giants in the asymptotic giant branch phase can be somewhat unstable, with brightness variations driven by complex interactions between multiple fusion shells. But even these variations occur over years or decades, not seconds or minutes. For main sequence stars, stability is the norm. Fusion proceeds at a rate determined by temperature, pressure, and the availability of fuel. As long as those factors remain constant, and they do for billions of years, the star shines steadily. This stability has profound implications. It means that planets orbiting stars receive a consistent amount of energy over time. It means that climates can be stable. It means that life, if it arises, has billions of years to develop and evolve in conditions that don't change dramatically. Earth's climate has certainly changed over geologic time, but most of that change has been driven by factors on Earth itself: changes in the atmosphere, the arrangement of continents, the circulation of ocean currents. The Sun's contribution has been remarkably steady, and this steadiness extends to the light we receive from distant stars. When astronomers measure the brightness of a star, they can be confident that the measurement reflects the star's actual luminosity, not some temporary fluctuation. When they observe a star over multiple nights, they expect to see the same brightness, unless the star is a known variable or part of a binary system. This predictability is what makes astronomy possible. If stars flickered randomly, if their brightness varied unpredictably, it would be nearly impossible to learn anything about them. But because they're steady, because their light is constant, we can make precise measurements, build models, test theories, and understand how stars work. The constancy of starlight is also aesthetically pleasing. There's something reassuring about looking up at the night sky and seeing the same stars, in the same positions, shining with the same brightness they've had for as long as humans have been watching. The constellations don't change over a human lifetime. The brightest stars remain the brightest. The patterns remain the same. This constancy gives the night sky a sense of permanence, a feeling that some things, at least, are reliable and unchanging. And in a certain sense, that's true. The stars you see tonight are the same stars your ancestors saw, shining just as brightly, just as steadily. They're the same stars your descendants will see centuries or millennia from now. Their light has been traveling through space for years or decades or centuries, and when it reaches your eyes, it delivers the same message it's been carrying all along. The star is there, it's shining, and it will continue shining for billions of years more. That's not poetic exaggeration. That's physics. Stars are stable, their light is constant, and that constancy is one of the most calming facts about the universe. The stars don't flicker, they don't fade, they don't change, they just shine. Stars rotate, not quickly in most cases, but steadily, spinning on their axes as they orbit through the galaxy. This rotation is a remnant of the angular momentum of the gas cloud from which the star formed, and it persists for the star's entire lifetime. The Sun rotates once every 25 days at its equator and about once every 35 days near its poles. This differential rotation, where different latitudes rotate at different speeds, is possible because the Sun is not solid. It's a ball of plasma, and different layers can move at different rates. When the Sun was young, it rotated much faster, perhaps once every few days. But over billions of years, its rotation has slowed, a process driven by the solar wind, a stream of charged particles flowing outward from the Sun. These particles carry angular momentum away from the Sun, gradually slowing its rotation. This same process occurs in other stars. Young stars rotate quickly. Old stars rotate slowly. The rate of rotation is one of the indicators astronomers use to estimate a star's age. Stellar rotation has several effects. It generates magnetic fields through a process called the dynamo effect, where the motion of conductive plasma creates electric currents, which in turn generate magnetic fields. These fields are responsible for phenomena like sunspots, solar flares, and the solar cycle. The Sun's magnetic field reverses polarity approximately every 11 years, a cycle that drives variations in sunspot activity and solar output. During solar maximum, sunspots are numerous and solar flares are frequent. During solar minimum, the Sun's surface is relatively calm. But even at solar maximum, the Sun's total energy output varies by less than 0.1%. The magnetic activity affects the Sun's appearance and its local environment, but it doesn't significantly change the amount of light reaching Earth. Other stars have magnetic activity as well. Some red dwarfs are highly magnetic and prone to powerful flares that can temporarily increase their brightness by factors of 2 or more. These flares are thought to be driven by the interaction between the star's magnetic field and its rapid rotation. But for most stars, rotation is a slow, steady process. The star spins, its magnetic field evolves, and over billions of years, the rotation gradually slows. There's no drama, no sudden changes, just a gentle decrease in angular momentum. Stellar rotation also affects the star's shape. A rapidly rotating star bulges slightly at its equator due to centrifugal force. The faster the rotation, the more pronounced the bulge. But for stars like the Sun, which rotate relatively slowly, the effect is minimal. The Sun's equatorial radius is only about 10 kilometers larger than its polar radius, a difference of less than 0.02%. Some stars, particularly massive young stars, rotate much faster. The star Vega, for example, rotates once every 12.5 hours, about 50 times faster than the Sun. This rapid rotation causes a significant equatorial bulge and also affects the star's appearance. Because the equator is farther from the center and moving faster, it's cooler than the poles and the star appears brighter at the poles than at the equator. But even fast-rotating stars are stable. They're not about to fly apart or lose mass catastrophically. The centrifugal force from rotation is far weaker than the gravitational force holding the star together. Rotation also affects how stars evolve. In binary systems, tidal forces between the two stars can synchronize their rotations with their orbits, a process called tidal locking. This is similar to how the Moon is tidally locked to Earth, always showing the same face. In close binary systems, both stars can become tidally locked, rotating once per orbital period. This synchronization can take millions of years, but once it occurs, it's stable. The stars continue orbiting and rotating in lockstep for the rest of their lives. Stellar rotation is one of those background processes that's always happening but rarely noticed. The Sun rotates every 25 days, but from Earth, we don't see any obvious effects. The stars rotate, but their light doesn't flicker or vary because of it. The rotation is simply there, a fundamental property of the star, persisting quietly throughout its lifetime. And like so many aspects of stars, rotation is predictable. Given a star's age, mass, and initial rotation rate, astronomers can calculate how fast it's rotating now and how fast it will rotate in the future. There are no surprises, no sudden changes, just slow, steady evolution, governed by physics, playing out over billions of years. The Sun will continue rotating for another 5 billion years, gradually slowing as the solar wind carries away angular momentum. By the time it becomes a red giant, it will be rotating even more slowly than it does now, perhaps once every 50 or 60 days. And even then, the rotation will persist. Red giants rotate. White dwarfs rotate. Neutron stars rotate, sometimes hundreds of times per second, but those are the collapsed cores of massive stars, not the fate that awaits the Sun. The Sun's rotation is gentle, steady, and persistent. It's been rotating for 4.6 billion years, and it will continue rotating for billions more. There's something calming about that. Stars don't stop. They don't pause. They just keep going, spinning slowly through space, carrying their planets with them, moving through the galaxy on long, predictable orbits. Everything is in motion, but the motion is orderly, governed by conservation of angular momentum, stabilized by gravity, predictable over cosmic timescales. The universe is not chaotic, it's structured. And the slow rotation of stars is one more example of that structure, one more piece of evidence that the cosmos is far more orderly than it might first appear. Around every star, there's a region where conditions might be right for life. It's called the habitable zone, sometimes called the Goldilocks zone, and it's defined as the range of distances from the star where a planet with the right atmosphere could have liquid water on its surface. Liquid water is considered essential for life, at least life as we know it, because water is an excellent solvent. It remains liquid over a wide range of temperatures, and it's abundant in the universe. So when astronomers search for potentially habitable planets, they look for rocky planets in the habitable zone of their host stars. The location of the habitable zone depends on the star's luminosity. A bright, hot star has a habitable zone far from the star. A dim, cool star has a habitable zone close to the star. For the Sun, the habitable zone extends roughly from about 0.9 to 1.5 astronomical units. That's from just inside Earth's orbit to somewhere around the orbit of Mars. Earth sits comfortably within this zone, and it's the reason our planet has had liquid water on its surface for billions of years. Venus, at 0.7 astronomical units, is too close. It receives too much sunlight, and its surface temperature is over 450 degrees Celsius, hot enough to melt lead. Mars, at 1.5 astronomical units, is near the outer edge of the habitable zone. It's cold, and most of its water is frozen, though there's evidence that liquid water once flowed on its surface billions of years ago when Mars had a thicker atmosphere. For red dwarfs, which are much dimmer than the Sun, the habitable zone is much closer. Proxima Centauri E, a planet orbiting the red dwarf Proxima Centauri, is only about 0.05 astronomical units from its star, about 1/20th the distance between Earth and the Sun. At that distance, it receives roughly the same amount of energy from its star as Earth receives from the Sun, placing it within the habitable zone. But being in the habitable zone doesn't guarantee habitability. A planet also needs the right atmosphere to retain heat, the right mass to hold onto that atmosphere, and protection from harmful radiation. Proxima Centauri is a flare star, and its frequent flares could strip away a planet's atmosphere over time, making long-term habitability uncertain. Still, the habitable zone is a useful concept. It narrows the search for potentially habitable worlds from trillions of planets to a much smaller subset, rocky planets in the habitable zones of long-lived, stable stars. Thousands of exoplanets have been discovered in recent years thanks to missions like Kepler and TESS. Many of these planets are in their stars' habitable zones. Some orbit Sun-like stars. Some orbit red dwarfs. A few orbit binary stars. We don't yet know if any of these planets harbor life. Detecting life on an exoplanet requires analyzing the planet's atmosphere for biosignature gases, molecules like oxygen, methane, or ozone that, in combination, suggest biological activity. This is extremely difficult because exoplanets are faint and far away, and their light is overwhelmed by their host stars. But the technology is improving. The James Webb Space Telescope, launched in 2021, is capable of studying the atmospheres of some exoplanets, looking for signs of water vapor, carbon dioxide, and other molecules. Future missions will have even greater capabilities. What's remarkable is that habitable zones exist around most stars. Red dwarfs, which make up the majority of stars, all have habitable zones, and many have planets within those zones. Sun-like stars have habitable zones. Even some binary star systems have stable habitable zones where planets could orbit both stars without being ejected or destabilized. This suggests that potentially habitable worlds are common in the universe. Not necessarily inhabited, but potentially habitable. Places where conditions might be right for life to arise and persist. And because stars are so long-lived, especially red dwarfs, these habitable zones can remain stable for billions or even trillions of years. Life on Earth took about 500 million years to go from simple single-celled organisms to complex multicellular life. It took another few 100 million years to develop intelligence. A planet orbiting a red dwarf could have hundreds of billions of years for life to develop. That's 1,000 times longer than Earth has had. If life arises and evolves at a similar pace, civilizations far older and more advanced than ours could exist on worlds orbiting red dwarfs. Or they could not. We simply don't know. But the potential is there, and it's vast. The existence of habitable zones also means that life, if it exists elsewhere, is probably experiencing a star similar to ours. A stable, long-lived source of energy, providing warmth and light in predictable amounts over billions of years. And that's comforting, in a way. If life does exist on other worlds, it's probably looking up at its own star, wondering the same things we wonder, seeing the same kinds of light, experiencing the same kinds of days and nights, governed by the same laws of physics. The universe is vast, but the processes are universal. Stars shine, planets orbit, light warms surfaces, water flows. And somewhere in that warmth and water, life might arise. It's happening around our sun. It could be happening around other stars too. And those stars will keep shining, keep providing energy, keep maintaining their habitable zones for billions of years, long enough for life to begin, evolve, and perhaps one day look up at the stars and realize it's not alone. There's a certain peace that comes from understanding stars, from knowing that they're not distant, mysterious lights, but rather objects governed by the same physics that governs everything else. Objects that can be studied, measured, understood, and predicted. Stars are vast, they're ancient, they're powerful, but they're not chaotic, they're not unpredictable. They follow rules. Gravity pulls inward, pressure pushes outward, fusion releases energy, heat radiates into space. The star shines. This process has been running for billions of years, and it will continue running for billions more. It's reliable, it's stable, it's calm. And when you think about that, when you really sit with the knowledge that stars are patient, enduring, predictable things, it puts human concerns into perspective. The sun has been shining for 4.6 billion years. It will shine for another 5 billion. Human civilization is about 10,000 years old. A single human lifetime is, at most, 100 years. In the lifespan of the sun, a human civilization is a brief moment. A human life is imperceptible. This isn't meant to diminish the importance of human life, but it is meant to offer perspective. The things that feel urgent, the worries that keep us up at night, the anxieties about the future, all of these exist on timescales that are infinitesimal compared to the timescales on which stars operate. The sun doesn't worry, it doesn't rush, it doesn't panic, it simply exists, converting hydrogen into helium, releasing energy, shining steadily, doing what it's been doing for longer than life has existed on Earth. And it will keep doing that, regardless of what happens to us. That might sound bleak, but it's not. It's freeing. It's a reminder that the universe is larger than our problems, older than our fears, and more patient than we could ever be. Stars offer a kind of cosmic calm. They remind us that some things are beyond our control, and that's okay. We don't need to control the sun. We don't need to manage the stars. They're fine. They're doing what they do, and they'll continue doing it long after we're gone. And in the meantime, we get to exist in the light of a star. We get to experience warmth, see colors, grow food, live lives, all because a star 93 million miles away is patiently fusing hydrogen and releasing energy. That's extraordinary. And it's also ordinary, in the sense that it's happening around billions of other stars across the universe right now. Life might be rare, intelligence might be rare, but stars are not. They're everywhere, and most of them are stable, long-lived, patient, calm. The universe is not hostile. It's not malevolent. It's not out to get us. It's just vast and old and filled with stars that shine steadily, creating pockets of warmth and light where occasionally conditions are right for something interesting to happen. We're one of those interesting things. We arose on a planet in the habitable zone of a stable, middle-aged star. We've existed for a tiny fraction of that star's lifetime, and we've used that time to look up, wonder, study, and eventually understand. And what we've learned is that stars are not gods. They're not mystical. They're understandable. They're physics, chemistry, gravity, and nuclear reactions. They're objects that follow rules, and we've figured out what those rules are. That understanding doesn't make stars less beautiful. If anything, it makes them more beautiful, because now we know not just what they are, but why they are, and how they work, and what they'll become. A star is a sphere of plasma, held together by gravity, powered by fusion, shining for billions of years. That's the simple version. But even the simple version is profound, because it means that the light we see, the warmth we feel, the energy that powers life, all of it comes from a process that's been running since before the Earth existed, and will continue running long after everything we know is gone. And there's something calming about that, something reassuring. The stars are there. They've always been there. They'll always be there, at least for a very long definition of always. You can look up at the night sky and see the same stars your ancestors saw, the same patterns, the same lights, shining with the same brightness, in the same positions, doing exactly what they've been doing for thousands or millions of years. And tomorrow night, they'll still be there. And the night after that, and 1,000 years from now. They're not going anywhere. They're too massive to move quickly, too stable to change, too patient to burn out anytime soon. They're just there, shining, quietly, steadily, calmly. And that's enough. Stars are patient, they're stable, they're predictable. They shine for billions of years, converting hydrogen into helium, releasing energy, lighting the cosmos. They're born in cold, dark clouds, collapsing slowly under gravity, heating up over hundreds of thousands of years until fusion ignites. They live on the main sequence for the vast majority of their existence, burning steadily, changing barely at all. And when they die, they do so gradually, shedding their outer layers, cooling over billions of years, leaving behind remnants that will persist for eons. The Sun is one of hundreds of billions of stars in the Milky Way. It's not special, it's not unique, it's a typical, middle-aged, main sequence star. And yet, it's the star that makes our existence possible. It provides the energy that powers life on Earth. It lights our days, it warms our planet. It's been doing this for 4.6 billion years, and it will continue doing it for another 5 billion. And beyond the Sun, there are countless other stars, each one shining in its own way, each one following the same fundamental rules, each one existing as a point of light in the vast, dark expanse of space. Some of those stars have planets. Some of those planets might have life. Some of that life might be looking up at its own star, wondering the same things we wonder, seeking the same answers. But whether or not life is common, stars certainly are. They fill the galaxy, the universe, providing light and warmth wherever they exist. They're the fundamental engines of the cosmos, the sources of energy that make everything else possible. And they do this quietly, steadily, without fanfare or drama. Just patient, enduring, reliable light. If you've listened this far, thank you. Thank you for spending this time with me, exploring the calm, quiet, beautiful facts about stars. I hope you found something here that brings you peace, or perspective, or simply a sense of wonder at the vast, ancient, orderly universe we inhabit. If you enjoyed this, I'd be grateful if you'd like this video and subscribe to Nebula Nights. There's more to explore, more to discover, more quiet corners of the cosmos to visit together. The stars will still be there tomorrow, and so will I, ready to wander through the universe with you again. Until then, rest well, sleep deeply, and know that above you, the stars are shining, just as they always have, just as they always will. Good night.